In this lecture, we will demonstrate the central limit theorem. So say that x1, x2, all the way to xn are IID random variables. They're independent and they all have the same distribution. The expected value is denoted by mu and the variance is denoted by sigma square. Then the central limit theorem tells us that the sample average, that is 1 over n summation, I go from 1 to n, xi is approximately normal with expected value mu and variance sigma square over n. This is not the central limit theorem in itself, it's a consequence of the central limit theorem, and this is typically how we use it. So in this first demonstration, each xi will be uniform between 0, 1, and then we'll have a look at the PDF of the sample mean and check if it's getting closer to the PDF of a normal. In this demonstration, I will use the statistics features in Maple. To use those features, you start by typing with statistics : Then I'm going to define my first random variable x1 by using the command random variable. It's going to be uniformly distributed between 0 and 1. Just to check that this works, I'll plot the PDF of my x1 random variable. U here is just a dummy variable. You can use any name you want to. And I want to plot the PDF from -1 to 2. Remember, the PDF of a uniform random variable is constant over its range. Since the range is between 0 and 1 and this area must be 1, the PDF is equal to 1 over its range. Maple can calculate the expected value of x1, and not too surprisingly, it's 1/2, which is right in the middle of the range. The variance comes out to be 1 over 12. So mu is 1/2 sigma square, which is calculated as the integral from 0 to 1 x minus 1/2 square dx comes out to be 1 over 12. So I have now defined my first random variable x1. So I'll create my second one, x2, also as a uniform, and then I can look at the mean of these two. So that's what I'm doing here. I'm defining my x2 also as a uniform 0, 1. And now I want to look at the PDF of the average of these two. So here I've done plot PDF. This is the average of x1 and x2. And what we see is that the average has this triangular shape. So even though x1 is uniformly distributed, the sample mean of two uniformly distributed random variables will not be uniform. As you can see, you have more mass around 0.5. So if you draw two random numbers from a uniform distribution, then the average is more likely to be around 0.5 than it is to be close to 0 or close to 1. I should mention also, by the way, that when you do this kind of thing in Maple, x1 plus x2, Maple automatically assumes that these two random variables are independent. To better understand this concentration of the PDF around 0.5, think about tossing two dice, where we calculate the sum of these dice. So the sum of two dice can be any number between 2 and 12. However, 7 is way more likely than 2 or 12. The probability that the sum will be 2 is 1 over 36. There is only one way of getting 2, and that is when both dice turn up 1. On the other hand, there are many ways of getting 7, namely 6 ways. You can have 1 on the first die, 6 on the second, 2 on the first, 5 on the second, and so on. So the number in the middle, 7, is much more likely than any numbers on the boundary, which is also what we see for the uniform distribution. So let's check if the approximation is any good when we are at just n equal to 2. The sample average with two observations should be approximately normal with expected value, well, mu in my case was 1/2, and the variance should be sigma square over n. Sigma square was 1/12, and I have 2 observations. Now, we wouldn't expect this approximation to be very good, as we have claimed that this approximation gets better and better the bigger n is, and now we are only at n equal to 2. So let's create a random variable with this distribution, plot it together with the distribution of the sample average with 2 random variables, and check if they are close to each other. That's what I have done here. I have created my y2 random variable as a normal with expected value 1/2. Maple wants the standard deviation, not the variance, so we have to put the variance inside a square root sign. So now I'm going to plot the PDF of the average together with this normal, and let's see what we get. So here the red one is the normal distribution and the blue one is the average of 2 uniform random variables. So you can see that even when n is equal to 2, the approximation isn't too bad. But let's move on. Let's define x3 as well, and then look at the PDF of the sample average of 3 random variables. So x3 is uniform 0, 1. The central limit theorem tells us the sample average with 3 random variables is approximately normal, 1/2, and now it's going to be 1/12 divided by n equal to 3. So I've created a random variable with this new variance, and here is a comparison of the sample average with 3 random variables and the normal distribution. You can see the approximation is even better. Moving on, defining a 4th random variable, a 4th normal distribution, comparing, better approximation, 5th one, comparing. The PDFs are getting almost identical. The 6th one, comparing. Now there's just a slight difference up here that we can notice. So I could go on, but beyond the 6th one, we won't even be able to see the difference between the PDFs. I'm only plotting the normal. The sample average will look exactly the same. Here is for n equal to 10. The PDF of the sample mean will have a distribution that's so close to this one that you won't be able to see the difference in this diagram. Notice how the distribution is getting taller and taller and skinnier and skinnier. So here is with n equal to 50, even skinnier, n equal to 1000, and what we see is that the distribution of the sample average does seem to converge to a spike as expected from the law of large numbers. Finally, I have done the distribution of the sample mean with 100,000 observations, and we are left with a distribution which has a width that we can't even notice. So as expected, even though the sample average is approximately normal for large n, when n goes to infinity, this converges in distribution and in probability to a constant mu. So in this demonstration, the approximation was really good even for small values of n. This is due to the fact that the uniform distribution is symmetric around the expected value. If you start with an IID sequence of random variables where the distribution is highly skewed, it will take a longer time for this approximation to work. So here is a second demonstration. In this demonstration, xi will follow a chi-square distribution with 1 degree of freedom. So I start by defining my first random variable as a chi-square with 1 degree of freedom. The PDF of this random variable looks like this. It's heavily skewed and not at all symmetric around its expected value, which is 1. The variance of the chi-square 1 is 2. I create a second chi-square 1, and here I'm looking at the PDF of the average of 2 chi-squares. It will look like this, goes like from 0 here, then up to 1, and then down like that. Doesn't look at all like a normal distribution. I can create the normal distribution, which is supposed to approximate this average, and that should have expected value 1 and variance 2 over n equal to 2. If I plot these two together, we see that the approximation is really terrible. That's the normal, that's the distribution of the average. However, as n increases, so I do a third chi-square and a third normal, plot the average of the 3 with the normal, we see that the approximation is definitely getting better. The red one is the normal, the blue one is the average of 3 chi-square 1. Here is the same thing for 4, for 5, and for 6. So even when we have the average of 6 chi-square 1s, the approximation is not all that great. But it does get better. If you do the same thing for, say, 30 observations, then you will have a hard time distinguishing between these two PDFs. So the final thing I want to look at is the central limit theorem itself. Remember, the central limit theorem doesn't say anything about the distribution of the sample average as n goes to infinity. It says something about the distribution of square root of n times the sample average minus the expected value of each xi. This one will converge in distribution to a normal 0 sigma square. So let's do a demonstration of this, where instead of looking at the PDF of the sample average, we look at the PDF of this whole thing, and we'll see that that is not going to go to a spike, it's not going to explode, it will converge to a nice normal distribution. So I return to the uniform random variable, to uniform 0, 1, and here is the normal 0 sigma square. That is, this is my y random variable. Remember, the variance of the uniform was 1 over 12. We need to put it inside square root sign because that's how Maple wants it. And here I have done, this is the sample average. I've subtracted the expected value, so that's xn bar minus mu, and I have pre-multiplied by square root of n. In this case, n is just 2. And we compare that to the PDF of the normal distribution. So now everything will be centered around 0. If I continue to do this with the third random variable, square root of n times the sample average minus the expected value. And in this case, it's exactly the same random variable y. We see that the distribution of this whole thing does converge to a normal distribution. Here's the case when we have 4, here's the case when we have 5, and here's the case when we have 6. This guy does not go to a spike. It goes to a nice normal with expected value 0 and variance sigma square, which is 1 over 12 in this example.